Ventura for normal state properties of layered bismuth-based superconductors, transport, and spectral properties. Please.
Okay, thank you. Well, hello everyone. Um, I would first start by saying thank you to the organizers for the invitation and for the hospitality to IIP Natal Institute. And well, thanks for your attention. I would like to tell you a bit about our work on the normal state properties of a set of non-conventional. Oh, what happened? Let me see. Non-conventional superconductors, which are based, they contain planes with bismuth and 2 sulfur ions, which are the conducting planes in these materials. And then there are also some blocking layers with other compounds, which I will mention. The work I will be telling you a bit about is work we have done in collaboration with José Querales, who was a former PhD student with me at Centro Atómico Bariloche and Instituto Balseiro in Argentina. We also collaborated in this work with Roberta Chitro from Salerno, Italy, and José Rodríguez Núñez from Venezuela. So let me just mention a bit. Well, this was the abstract. Basically, what we mentioned there is the compounds were discovered in 2012. And the interesting thing is that I will show you in a moment that the crystal structure of these bismuth S2 layers is quite reminiscent of the layers you have in the cuprates, copper-2 planes, or the planes with iron and different arsenides or chalcogenides in pnictides and chalcogenide iron-based superconductors. But there are other properties which are different. And there have been many discussions, of course, quickly when they were discovered about the origin, which could be the mechanism for the superconductivity. And there are many indications that the electron phonon is weak, even though the TC is relatively small, as I will show. Electron phonon is weak to provide the kind of coupling which would result in the phase, the superconductivity seen. And there have been many different proposals, among them the effect of electron correlations. So I will be talking, this is the kind of approach we are looking into. And then I will show you a bit how we used a model, a simplified model, including the effect of electron correlations to describe normal state properties of these compounds. In particular, I will show you our results on spectral properties, resistivity, and Hall coefficient. And since there are many experts in the audience, it would be nice if when you see the data, you would like to tell us some comments, especially the transport and the Hall coefficient part. The newest results. So we're still thinking a bit about what is really happening there. But they're describing quite well the experimental results, which we could find. The spectral properties we have already published in this paper in 2016. And so let me just start a bit with a talk. So as an outline, basically, well, we already started giving a bit of introduction, what might be the interested in studying these materials. And basically, what we want to do is to be able to describe properties which depend on temperature, doping, and crystal momentum, which our approach allows us to do. And then I will just give a very pointed introduction, reviewing a few previous results. Recently, there has been a new review published this month by the people who, Mizuguchi and his group, who actually discovered the compounds. And they have already about 220, more than 220 references. So, of course, I will be choosing a few related to what I'm going to talk today. And well, with our approach, what is interesting, we can, which is based on using 2 correlated effective orbitals and a treatment for these correlations, which are intermediate in these materials. So we can obtain a second order in perturbations on the correlation self-energy, which has this temperature, doping, and K dependence. That's interesting because we can describe spectral properties like the spectral density function as a function of K, and that's what we already published in this paper, which is there in green. And today I'm also to show you the newest transport results, and then I will just conclude and tell you a bit our outlook. So this is just a very quick, nice picture in a review on superconductors by Hirsch, Maple, and Marsilio, 2015, where they put a bit about 32 classes of superconducting materials which were surveyed and were classified depending on if there was evidence for the mechanism for superconductivity to be conventional, possibly unconventional, or unconventional. And as you see, here you will find, for example, the pnictides, the cuprates, and down here in 2015, they put bismuth S2 compounds as possibly unconventional, and they more or less remain in categories, although there is more evidence that electron phonon is not strong enough, so they more than possibly, they are possibly now unconventional already. So let us very quickly mention, this is, for example, the kind of crystal structure you find in these compounds. And this is a paper by Mitsuguchi where they started, where they first found the critical temperature of 4.5 Kelvin. It was actually in this compound. And then very quickly, let me go to the next slide. Very quickly, in the same year, Mitsuguchi also, this is the first compound they found. Here you will see these are the planes which have this bismuth, this is the violet things, and the two sulfurs connecting each bismuth. And these bismuths form like a square lattice on planes. And these planes are intercalated between blocking layers of other atoms. And then, for example, very quickly, the same year, this other family was found, where here you, for example, have lanthanum, and you could dope this material. And, for example, they found that the critical temperature could be increased in this material, applying, for example, 2 gigapascal of pressure, would go to 10.5 Kelvin. And so actually, and with this material, they could, with lanthanum, they could actually prepare good single crystals. So many other experiments were available and results obtained. And here you see how the family has grown. So very quickly, here you see the first two compounds I was showing you are these ones. And for example, one of these, let me see. Well, where is the... here you would have in the rare earth, you would have the lanthanum here. This would be the other one in 2012. But then you see this kind of layers. These are the blocking, the conducting layers with bismuth S2, sulfur 2. And then you have all these other kinds of blocking layers, which depend a bit more on the material. And more recently, there have been also some other kind of doping in which they are doping into the sulfur, and, for example, including chalcogens, like selenite. And what they found is that the superconducting properties are not reduced too much, and not affected too much, but they can, by putting that kind of doping, they can obtain, let's say, functional materials with nice thermoelectric properties. So that's also some interesting, let's say, detour from these materials and possible applications. Well, here you see, just put this just to see that it's the same kind of things. Oh, sorry. You saw in the iron pnictides, you have these kind of iron arsenide planes, and in the different, some of the different materials of the family, depending on the blocking layers, you get other properties, and of course you get different critical temperatures, etc. But actually, there are some similarities in the kind of crystal structure in these compounds. And this is actually, I put this because it's a recent paper by Cobo Lopez, Arita, Eremin, and some other colleagues this year, which is interesting because they review a bit how is the situation with all the other mechanisms which were at some point analyzed as possible sources of superconductivity. And as you see, the latest things are you can no isotope effect is found. Also, with the latest ab initio approaches, they don't see, for example, in this compound, strong enough electron phonon coupling to describe the superconductivity here found. And there were different kinds of processes investigated. But, well, in all, let's say the superconductivity is not yet clear. So it's still under discussion. I will tell you a bit later, eventually, about this paper. But this, for example, down here is another paper in ARPES, where they also find in ARPES evidence that really they believe that the evidence is showing that they are unconventional superconductors. So in that sense, there has been progress in that sense. So here, let me show you just a bit the kind of band structures obtained from DFT for these compounds. These, for example, appear in a review by Yassisi and other people in 2015. For example, well, the parent compound, for example, for this one, which I was telling you, good single crystals are obtained. The parent compound is an insulator, band insulator. Some people say it's semiconductor, but in principle, according to the results and most evidence, it's band insulator. If you change oxygen by fluoride, you obtain a metal. And the compound, which has the best, highest ITC found in this family, is actually when you dope half of the oxygen with 50% fluoride. And there you obtain this kind of bands crossing the Fermi level. And here you see the density of states, and you see the character of the bands, which are, is this pointing? Yes. Character of all the bands which you are seeing here. And in principle, one can see that the main bands near the Fermi level are related to bismuth p orbitals and sulfur p orbitals. And so, of course, there has been some kind of a downfolding approach. Well, this is just a very pictorial view of the kind of doping I was mentioning. In the blocking layers, you have the oxygen, and you can just change one oxygen by a fluoride, and then you free one electron, which goes to the conduction planes. And so that's a way to dope with electrons those planes. And there have been many other studies of other substitutions. But going back to the band structure, there has been actually here, this Usui, Suzuki, Kuroki, in 2012 already. From those DFT calculations, they did some downfolding and obtained the band structure, which here is shown as bare bands in black, these two curves, which are, let's say, the main things we were seeing near the Fermi level in the other picture, right? And here, I already added some of the things we used to try to include the correlations. And for example, what we did was, as I will quickly show here, what we did was taking into account all what was known, let's say in 2016 actually for the bands. We wanted to study these properties, so we took as a minimal microscopic model the Usui orbitals, which were uncorrelated in principle, obtained from the DFT, and then we added local correlations, intraorbital and interorbital, and analyzed the effects. How? Well, we did the green function calculation. There are evidence of many works that the correlations are not very large, so this kind of scheme should work well, and actually it does improve the results. And we could determine, as I will briefly mention, perturbatively the second order temperature-dependent electron green function for these two effective orbitals. From there, we got the self-energy, and from there we can, of course, start looking at the spectral function and compare with ARPES results. And we also, I'll just mention what we did for the transport. But so in principle, what we did was that, starting from those bands, add correlations in this way. So in principle, what we do is we take a Hamiltonian where you have one place, these are just the bare Usui bands obtained from the downfolding from DFT. We added local intraorbital correlations, and these are local interorbital between the C and D, we call the two orbitals, correlations. And here I mentioned the bands. Actually, we had applied also this for the nictet compounds, and I told a bit about those results when I was 2 years ago here in Natal. So basically what we did at that case, we used other bands by Rago, Scalapino, etc., for the iron nictet to look at the spectral properties. And this time we used for this lanthanum oxygen fluor bismuth S2 superconductor. So let me just quickly say how we determine the electron Green's functions through this calculation. Basically, once I will just show in a moment basically a very little thing about the Green functions. But once we have the Green functions, taking the imaginary parts, we can quickly obtain the spectral density contributions from each of the two bands, the total spectral density, and then we also have a self-consistency condition for the chemical potential and the total number of electrons in these bands. And how do we get the Green functions? Well, we use the Suvarev approach of equations of motion, which is, these are Green functions which are defined as a function of temperatures. So they depend on mean values at the finite temperature. And what we did was use the equations of motions for those. In principle, we have one for the C band of electrons, another for the D band of electrons. And with these other terms in the equation of motion, they are coupled to higher order Green functions. And there you can decide where you would like to, I don't know, decouple the equations and finish. And there you get different approximations for the results. If you do the first order approximation, you will just end having Hartree-Fock result. So let me see. This is, for example, the kind of Hartree-Fock result you would get. I mention it because for the transport, actually, we did use the Hartree-Fock result. So we did not need to use. For the spectral properties, actually, no. We went a bit higher to be able to describe reasonably the spectral function. So to go higher, we have to look at the higher order Green functions coupled to the two Green functions we are interested in. And for those, we also had to calculate their equation of motion and decoupled in their own. So you obtain further higher order Green functions. And there we do the decoupling. And we end up with two RPA-like solutions. But in truth, the second order equations have more things than the normal RPA Green functions or approximation. Well, and from these things, which depend on all the dopings or the mean values of the occupations of the different bands and temperature explicitly, and you have also double and triple sums on the Brillouin zone. We can calculate with this approach the Green's functions. And here, for example, I show you some of the results we get. Here on the right side, you see some calculations done by Usui with the bare bands. And actually, the Fermi surface they obtain describes quite well what is known from the materials. And these are as a function of increasing doping. So this is 0.2 doping in this lanthanum oxygen fluor bismuth S2. And here you have, for example, you notice that you're having a topological change of the topology of the Fermi surface. No? In this case, it is doping 30% and 40%. So with these bare bands, they get a critical doping where you get this Lifshitz transition. And then when you have more electrons, the Fermi surface doesn't change much more. So, I mean, it conserves. This is the calculation by Usui. This is the calculation by another group, Ye and other people. This was from, I don't know, here it says the whole reference, 2014. They did also the band structure calculations and the Fermi surface. And again, this for neodymium, also with 50% doping. And you see that something quite similar happens. So you have, for smaller dopings, you have this kind of smaller Fermi surface. And then at some point, you have a transition to this larger Fermi surface. So that's a feature which is common. With our Green functions, we could also look at all the Fermi surface, etc. And here, for example, I just mentioned that's a function of doping. In the bare, this Usui features, actually the transition is placed at about 0.4, while introducing moderate correlations shifted to lower doping. And for example, you get about 35% critical doping in our second order approach. And if we do Hartree-Fock, you get it at 22%. And this is for this kind of 1.5 intraorbital correlation, and this is half the interorbital. Sorry. Okay, sorry. Well, well, okay, so here I want to just to show that we obtain results for the Fermi surface, where you see that if you have the uncorrelated band, you have this, and when you start including the effects of correlations, you increase the nesting. So that's also some of the kind of approaches some other people were proposing were relevant in these materials. Our second order approach for the spectral properties also allows us to compare the results we get for the chemical potential shift as a function of filling. And actually, this point is the result which was obtained in photoemission. And we are comparing with, this is DFT. So DFT alone is quite far away from the experimental point. The two orbitals by Usui, let's say the bare band structure, give you this kind of chemical shift as a function of doping. And when we use the R approach, including the correlations, you start getting really very close to the chemical shift. So actually, it's capturing that, which is actually something quantitative. And then we did predictions for the density of states as a function of doping. Well, this is something else I will not enter into now. These are the kind of results we get for the spectral density function along different lines. This is near point X of the Fermi surface, X and gamma path. And this is the effect on the Usui bands without correlations, and this is with a second order approach, which when we compare with Terashima's ARPES results, these red results describe much better what is really found there. And let me just very briefly mention the latest results we had done before a calculation of transport, magnetotransport for iron chalcogenides. And actually, in that case, we could describe quite well, if you see here, in a similar approach to what I have been discussing. Oh, sorry, not this one. Well, I'm having the same trouble of many speakers. The buttons are too close. So here what we are having is magnetoresistance as a function of magnetic field. And we are comparing with data which were measured in the low temperature group in Bariloche for these chalcogenides and our calculation. So you see the fit is really good. And we don't have many parameters because we are having all the band structure comes from Usui. So we are just plugging in this correlation value, which we are also not modifying. We're using the same which we used for the spectral properties. And then we also looked at the Hall coefficient, but also that could describe quite well. I'm not interested in that. Let me just mention, because of the time I have, that how do we do the calculation of the transport? We are basically using linear response correlation functions, and we are using the Kubo formulation to obtain the different components of the conductivity tensor and the resistivity. And then we can, having this transversal conductivity, also obtain the Hall coefficient. Let me just quickly go to the results. This is for the, well, again, the same picture of the bare bands and Hartree-Fock, and the red ones are the ones in second order. For the transport, we believe that we would be successful also describing it just at Hartree-Fock level, and I will show you it really works, even as it did for the iron chalcogenides. And this is just to, to show you in the bare bands where the Fermi level would lie for some of the fillings I'm going to show now in the transport results. So this is a result we obtained, for example, for resistivity, in-plane resistivity. And here you compare the points are the experimental things for two dopings. You have the 0, so the parent compound, which is semiconductor-like, and 0.5 is the one which has the optimal TC. And we also put some intermediate 0.3 doping. And as you see, actually, the description of the experimental points, which we found for this compound, is really very good. Even with two kind of small small correlation values. This one is smaller because it has to do with this other experiment calculation I was telling you about Eremin. But you see, it's almost equally good describing it with this U 0.6 or 0.1. So here you see that they fit very well. And here also it's reasonable. Actually, it's better when you have some doping. Here I wanted to show how you improve the description by including the correlations, because it was a discussion with these materials. And here you see very quickly down there, if you use the uncorrelated resistivity result, it's quite far from the one when you have the correlations. So there, the fit to the experiment is very good. Let me show you, this is the kind of Hall coefficient results we're getting. And again here, you see, you have the yellow dot dash curve is actually for uncorrelated case. And when you're, and this is actually for another material, we couldn't get Hall coefficient results for the lanthanum one, but this is what we got. So we can really do the calculation with the doping and touch the things to adapt it. And so here you see that actually the description of these open points, which are the experimental results, is better for some intermediate value of correlation. Not to the smallest one, not the larger one, not the uncorrelated. So this is something which I would like to talk to some of the people who are here in the audience, expert in Hall coefficient, Hall measurements. But actually we believe it has to do with this kind of multi-band character of the electrons which are intervening in the transport. And so, well, basically here are my conclusions, which I can very quickly say that with our approach, looking at this compound, which is the one with the optimal high TC in these materials, we could get a quite reasonable description of the spectral properties and even the first transport properties we are looking at. And what we find is indeed that correlations are needed. Moderate correlations are the ones who improve the description. If you don't put them, you have some problems. If you put them too large, you also have problems. So it's nice that we are finding this. And our idea would be to continue looking at other properties. We have the green functions. We can tune doping, temperature, etc. So there's a lot of work we can do. I leave it just not to overstep too much my time. So thanks, everybody. And that's it.